Welcome back, everybody. We saw last time that the curvature kappa is equal to the length of capital T prime of t divided by the length of r prime of t, which is also equal to the length of r prime of t cross r double prime of t divided by the length of r prime of t cubed. So let's do an example here. So let's say C is a curve given by the vector function out of t, which is equal to t comma t squared comma t cubed. We want to find the curvature kappa at the point 0, 0, 0. Now clearly the point 0, 0, 0 belongs to this curve because out of 0 is 0, 0, 0. So let's compute r prime of t. R prime of t would be derivative of t, which is 1, derivative of t squared is 2t, derivative of t cubed is 3t squared. R double prime of t would be derivative of 1 is 0, derivative of 2t is 2, derivative of 3t squared is 6t. So this is r double prime of t. So now since we want to know the curvature at this point. Now this is the point. This is the point that is traced when t is 0. So out of 0 is that. So what is r prime of 0? R prime of 0 would be 1, 0, 0, and r double prime of 0 would be 0, 2, 0. Notice that the length of r prime of 0, so this is the length of this vector here, would be 1. And now we take the cross product of r prime of 0 and r double prime of 0, which is equal to the determinant of ijk 1, 0, 0, 0, 2, 0. And if we compute this, we get 2k, which is the vector 0, 0, 2. So the length of r prime of 0 cross r double prime of 0 is equal to the length of 2k, which is equal to 2. So what is the curvature at t equals to 0? Well, it is the length of r prime of 0 cross r double prime of 0 divided by the length of r prime of 0 cubed. And we computed the numerator to be 2, and recall that we also computed the length of r prime of 0 to be 1. So we got 2 over 1, which is 2. So the curvature curvature here the curvature of this curve at the point out of 0 is 2. Okay, so let's say now that I have the function, I have the curve C, which is the graph of the function f of x. And the question is, how do I find the curvature of the curve at the point x comma f of x? Well, we can even though this is a curve in the 2 space, we can parameterize that as a curve in the 3 space in the following way. So we have this point x comma f of x. So we're going to define the vector function out of x to be the point x comma f of x comma 0. So then this curve C here would be the same curve here, except that this would be in dimension 3. This would be in the xy plane, right? So but the curvature doesn't change just because I'm drawing this in the xy plane in the 3-dimensional space. So now I can calculate I can apply the formula for the curvature. So we know that the curvature at x then would be r prime of x cross product with r double prime of x divided by the length of r prime of x cubed. And if we compute this ratio, what you're going to find out is that the curvature at x is equal to the absolute value of f double prime of x divided by 1 plus f prime of x squared to the power 3/2. So if I have the graph of a function y of x, where y is equal to f of x, then the curvature of the curve at x is given by this formula. So here's an example where we're going to apply this formula in red. So let's say I have the function f of x equal to x squared, and this is the graph of that function, and I want to find the curvature of this parabola at the point 1, 1. Well, the derivative of that is 2x and the second derivative is 2. So the kappa, the curvature at this point where x is 1, so the kappa of x would be, remember, the absolute value of f double prime of x, which is 2, divided by 1 plus f prime of x squared, so and to the power 3/2. So this would be 1 plus f prime of x squared, which is 4x squared, to the power 3/2. So we are applying this formula right here. And so the kappa at 1 would be 2 over 1 plus 4 times 1 here, so that's 5 to the 3/2. And this is approximately 0.18. So the curvature of the parabola at x is equal to this, and the curvature at 1 is equal to approximately 0.18. Okay, so I am going to stop the video here, and in the next video we will be computing the curvature of a circle. See you then.